And now we move to our second episode for today, which talks about AI's impact on the environment. We begin with the wonderful Kate Saenko, Associate Professor of Computer Science at Boston University. Kate is a leading expert in efficient, adaptable, and explainable AI. She'll be talking about addressing the high energy costs of learning in AI systems. I invite you all to head to the next page with the same title, and I'll give the floor to Kate.
Hi, I'm Kate. I'm very happy to be here. Um, and I'll be talking about the energy costs of artificial intelligence systems. So, first of all, I want to talk a little bit about what is machine learning and artificial intelligence and what makes it so power hungry, shall we say. Um, And then I'll talk about a few solutions, including some that we're looking at in my research lab at Boston University. So let's start with what is machine learning. Now, I'm sure most of you know already, but just to have a brief refresher, a machine learning algorithm is a software algorithm that learns how to make decisions from examples. So instead of hard coding a machine how to do something, with a machine learning algorithm, we show it examples and it learns how to make decisions based on examples and then the decisions that humans made for those examples. So let's take, for instance, a digit classification task. Here, the data set of examples that we need is a data set of pictures of digits, handwritten digits, and the algorithm takes one image of a digit and tries to predict or classify it into a set of categories. So in this case, the digit is a 2, so the algorithm has to output that this is a number 2. Now, the learning is actually what we call a training phase. So the way that an algorithm learns is it cycles through a lot of these examples from its data set. And in the process, it makes some mistakes. So for example, when we start out, the algorithm might take this picture of a 2 and classify it as a 3, so make an error. But that's how it learns. So it learns by making mistakes and correcting its own mistakes. So after correcting itself, it updates its own internal state, and eventually, after looking through lots and lots of data, and correcting its mistakes on lots and lots of data, it will learn to make good predictions. So at that point, we stop training, the training phase, and we start the testing phase, which is deployment. So we take that algorithm, we deploy it, we show it new inputs, and it will predict classes of digits in this case. It will make predictions on those new inputs in the wild. So in terms of the cost, the power costs or the energy costs, I would say most of the costs will be associated with the testing part. So this is when we actually use the algorithm. If we're deploying it in our system in a product or in the back end of some system, it's going to be most of the time using it, right, at testing time. But I'll also talk about the training costs because, as we'll see, the training costs of artificial neural networks, especially this type of algorithm I'll talk about, are getting very high. So, all right, so I already mentioned neural networks. This is by far the most popular algorithm right now that people use, I would say, at least for highly complex structured data like images, text. And it has kind of connections to the brain. It's inspired by the brain, by neurons in the brain. But these are artificial neurons, so you'll see essentially layers of neurons. Each of these neurons is a weighted combination. It computes some, it multiplies its inputs by some weights. So we think of these as synapses in the brain that connect neurons in the brain, and then it predicts the output. So the learning part of training a neural network is essentially learning these connections. And so here I'm showing the connections with different thickness to indicate that some of them will have lower weights, smaller weights, and others will have higher weights. So it's this process of learning how large the weight is for each neuron that connects to the other neuron in its previous layer. That's what we learn while we're training the network. Okay, so very brief neural networks. Now that was for images. We can do the same for text. So we just take our sentence or a paragraph or some piece of text and feed it into the neural network, and it learns to make decisions or learns to even generate sentences. It can generate paragraphs as well. So it learns how to process text as well from examples. Okay, so now that we've seen briefly what machine learning is, let's talk about why it takes so much computing resources to get it to learn and to operate. So the real problem with it is that the larger networks turn out to do much better in many cases. So for text processing and for image processing, video processing, the more neurons and the more of these weights, these connections that we have in a neural network, the better it will perform, the more accurate it will be. And in the recent few years, the field of neural networks and artificial intelligence has discovered that the larger we make them, essentially the better they work. So we keep making them larger. For example, BERT is a type of an AI model that learns from language, learns to process text, and it has 340 million connections, these weights, these connections between neurons. So that's a very large network. If you can imagine 340 million parameters that we have to learn and store, and then every time we apply this network at test time, we have to make that many computations. So that's why it takes a lot of power. Now you might be wondering, how does this compare to humans in terms of both accuracy on certain tasks, but also in terms of the size of the network? So this is a benchmark, a test of AI called RACE, or the Reading Comprehension Test. So here, both humans and AI models are tested on essentially English exams. These are real English exams that are given to middle and high school students, and they are evaluated on how well they do on these exams. So they read some text and then they answer some questions. And you see that the human ceiling performance, which is, you can think of as a good high school student, a motivated high school student, is around 94.5% accurate. Now, this model I just talked about, BERT, is around 72% accurate with 340 million weights. In the human brain, by some estimates, there are somewhere on the order of 100 trillion weights. So this AI model is much, much smaller than the human brain. But these, of course, are not accurate comparisons, but just to give you an idea of scale. Now, human low performance, this is, you can think of it as an unmotivated high school student. So these are workers that kind of are asked to do this task, but they're not very motivated to do it well, so they don't do nearly as well. But you can see that the AI is very close to essentially an unmotivated high schooler on these comprehension tests. Now, this model, by some estimates, can take a lot of power to train, and in the process of training it, which I explained earlier, it can generate as much carbon emissions as it might take to build and drive 5 cars over their lifetimes. So that's just to give you an idea of how much energy it could take to train a model such as BERT. So that's quite a bit of power. This is during training time. Another, just an idea, another comparison that people have made is to train BERT once, so that means we train one BERT model. Of course, we can train multiple BERT models, but just to train one BERT model, that can take as much power or generate as much carbon footprint as a single passenger flying a round trip between New York and San Francisco. But during the process of training, we usually train models multiple times because we often don't know, for example, how many layers or how many connections, what size we actually need for a task. So we tend to vary these aspects of the model and train multiple versions and then pick the one that works the best. And so in the process of doing that, we might train that model 40 times or 100 times, and then we're approaching the carbon footprint of an entire passenger plane flying between New York and San Francisco. So that's just to give you some idea of the energy cost involved. Now, these models are also not very data efficient compared to humans. So when we train BERT, BERT was trained on around 3.3 billion words in the data set. Because it's a language model, it was trained on a data set of text, mostly text taken from the web. Well, all of it is taken from the web. And the size of that text data set was 3.3 billion words. But while training, I mentioned earlier that the AI model has to go through and look at the data multiple times to keep correcting its mistakes. And so during learning, it actually looks at these 3 billion words 40 times. And then if we compare, an average child might hear about 45 million words by age 5. So that's 3,000 times fewer words than BERT had to see before it became trained. And of course, like these, again, comparisons are not exactly accurate because these are, we don't know exactly how many words a child might hear, and this is a 5-year-old child, not a high schooler, but just, again, to give you a sense of scale here. So AI is not very data efficient. But these models, like I said, they're getting bigger and bigger in size, so the number of weights is getting larger and larger. And recent models, so BERT was now at this point a few years ago, and you can see on this graph the size of more recent models compared to BERT and ELMO, which were the earlier kind of large-scale models of this type. I mentioned that BERT has, one version of it has 340 million weights. The more recent ones, like GPT-3, have several hundred billion weights. And the Megatron language model that was recently released by NVIDIA has up to 600 or 530, I think, and up to even 1 trillion weights. So they're getting very, very large compared to BERT, much larger. So you can imagine what effect that has on training. Of course, researchers are also coming up with more efficient ways to train these models, but it's still, the scale of it is much, much larger. And you'll also maybe notice that the names for these AI models is evolving from these kind of cute names like Elmo and Bert, Sesame Street characters, to more recently names like Megatron, which are sounding more, I shall say, intimidating. So I'm kind of curious now, what is the next model that we'll see, that what it will be called? You can imagine certain dystopian movies after which it might be called. But yeah, the point is that there's this very steep exponential trend in size. And if we go back to this comparison between the human performance of kind of the motivated student versus the unmotivated student, and if we look at now the Megatron version of BERT, which is larger, it's like BERT, but it's about 10 times larger. It has 3.9 billion parameters. It is now getting 90.9% accuracy on the English reading comprehension test. So it's actually getting close to the human ceiling performance. It's doing much better now than the unmotivated high school student that we saw the smaller version of it um, working at that level. So size is affecting performance, at least in these models for language comprehension, for language processing. Now, image models, so these are AI models that do object detection or process video or images in some way. These are still much smaller than the language models, but they are also catching up. So on this graph, I'm plotting the size of BERT just for scale for comparison and comparing it to the sizes of recent image models that have been coming out in the research field. So ResNet 152 is smaller than BERT, but ResNext 101 is larger. More recent ones are transformer type models, which are even larger. So you see the last one, VITG, is a transformer type of model reaching 2 billion parameters. So again, vision is smaller, but catching up in size. Okay, so we've seen that AI models are large and getting larger, and this drives the high cost, power cost of both training and deploying them. What are some solutions that we can do, we can make to reduce this energy cost? So the first solution is essentially pruning the model size. So in these networks, I showed you earlier, the weights are not all equal. There are some very small weights. So one idea is maybe we can essentially prune parts of the network that have small weights and end up with smaller networks or subnetworks of the original one. And that is exactly what pruning does. So this is one of the popular approaches to reducing the size of the network. Now, this can be done after training. So once we've trained the network, we prune the low weight connections and nodes, and then our network becomes smaller so that at test time when we deploy it, we have a smaller runtime cost. But this doesn't really work well at training time. So at training time, we still need to train a very large network that we later prune. So this reduces the energy cost at test time, but not at training time. Another approach, and this is something that we're working on in my lab, is network quantization. So you might have seen quantization in images and color compression, for example. So on the left, you see the original image, which is stored using 32-bit integers for each color. So this is a lot of bits, and you see a very high quality image. We can quantize it very severely and store each pixel color in just 2 bits. So it's very little. It's just 4 options for each color, but you still see that you can make out it's a flower and it's on some green background. And if we go up to 4 bits on the right, we get more detail. It's even a little bit better. But the point here is that we can quantize information and still retain a lot of the semantics, a lot of the meaning. So in quantizing neural network weights, so we can apply this idea to reduce the storage and power needs of a network by quantizing the weights. So instead of storing the weights using 32 bits of information, we can store them using 8 bits, 4 bits, or even 2 bits. And so this is what we did in our work. This is a recent paper that I co-authored called Dynamic Network Quantization, and it proposed a model called Video IQ, which is a dynamic quantization network. So in traditional video recognition, we take a video, we extract frames from the video, as you can see here, and we feed each frame into a network. Let's say that original network has 32 bits to store its weights. And after processing all the frames, the network predicts the category of the action that happened, that it thinks happened in the video. Now, in our approach, we save computation by essentially dynamically deciding how many bits the network should use. So it could use 4 bits for the first frame, and then even lower, only 2 bits for the next frame. And then it could decide dynamically that for the third frame, it needs very high quality information. It has to look at that image in kind of more detail to figure out maybe this is a frame that is very discriminative and really shows what the action is. And then for some later frames that maybe are less relevant, it could even decide to skip them altogether. And so in the end, this reduces computation because we are using fewer bits and we're also skipping some frames. Here's another example. We have a video of snow tubing, and it's skipping some of those frames and using lower bits for others. Here's another example of mixing drinks. Here you'll see the network also skipped some frames and used high bits for some of them, like the one that has the cup in it. And just to compare the accuracy, so here on the x-axis, I'm showing gigaflops, so basically the amount of computation it takes for the network to process videos. And on the y-axis, I'm showing the accuracy, essentially. So higher is better. And you can see that our video IQ model is more accurate and also takes less computation than these competing methods. So just to summarize what I talked about, we've seen that AI is very power hungry because the models are quite large and they take a lot of time to train, and also because of their size, they take a lot of power at test time. And we've seen a couple of ways to reduce that power consumption at test time with network pruning, for example, or network quantization into a smaller number of bits. I haven't talked about other ways, other popular ways such as distillation and weight sharing. But just to mention it, there are a couple of other ways that people use. But again, mostly at test time. So we still have to train a large network and then shrink it down to a smaller size afterwards. And the last thing I want to mention is, the reason that even though training happens kind of once or a couple times, but that's not most of the lifetime of a model. Most of the lifetime of a model is testing. But I still think that training cost is important because of even the monetary cost. For example, by some estimates, to train this language model called T5, it might have taken something around $10 million of compute cost to train this 11 billion model. So this can affect even access to AI models. Who can train these models? Who can afford to train them and develop them? But that's all I wanted to talk about, and I'm very happy to take questions. I'll stop here. Thank you.
Thank you so much, Kate. We have time for 2 questions, I think. So we have one: what is the outcome of reducing the model size on the efficiency of the systems?
So the smaller the model size, the more efficient the system will be. So it's a direct relationship. So if you can make the model half the size, it will be, I don't want to say twice as efficient because there are other hardware constraints, and because you have to be able to also implement some of these reductions in hardware efficiently. So for example, using smaller number of bits in hardware. But in general, if you just make the network smaller just by making the whole network half the size, it will be roughly twice as efficient.
Okay, another question is, some journals now require researchers to include the energy consumption of their AI models. What do you think about this, and what other measurements you think could be taken to address this issue?
Yes, I think that's a good trend because, as I mentioned on my last slide, sometimes large research groups from industry publish models that are very expensive, took a lot of power, a lot of cost to make. And this makes AI less democratic in the sense that there are only really a few entities in the world that can afford to do that. and to, to participate in creating these AI models. So I think it's important to make that more upfront and more known what it took for your model to be trained in terms of power cost. And I think test time cost is important to report, but also training time cost is important to report. Sometimes people don't report that. There's a lot more research I see into reducing the test time cost, but not training time cost. And I think also reporting everything. So not just how much it takes in theory to train your model once, but also how many times it was actually trained, because sometimes it's trained many, many times, like I mentioned. So reporting that, I think, makes things more transparent to just reproduce somebody's results from the literature.
Great. Okay, we have to wrap up, unfortunately. Thank you so much, Kate, for joining us in time today.
And it's great to be here. Thank you.
Have a great day. Bye.
Bye.